Does this series converge or diverge? Well, if you look at just this part, 4 to the n over 3 to the n, that could be rewritten as 4 over 3 to the n. That's a geometric series, and the r, 4/3, is bigger than 1, so it diverges. Then, by having this extra n in the denominator, is that enough to salvage it? In other words, you're now dividing by even more, since you've got n down there. But is that enough to overcome a 4 to the n? I seriously doubt it. That exponential function is a lot more powerful. So my guess is that it diverges. Then, how can we show that it diverges? Well, I could try a comparison test. I would need to show that it's bigger than or equal to something that diverges, because then you're showing this one is bigger than or equal to something that adds up to infinity. So that means it would add up to infinity. But what could I use? Because I've got this mixture of exponential functions and algebra n. Well, I could also use something like the ratio test. But you know what? One of the very first things that we had with series is if this is not the sum, but just the limit of these terms doesn't go to 0, then it's going to diverge. So take the limit, as n goes to infinity, of the individual terms. Right now, that's of the form infinity over infinity, so I'm allowed to use L'Hopital's rule. So it's going to be the limit as n goes to infinity. The derivative of 4 to the n is 4 to the n times the natural log of 4. For the bottom part, we would need to use the product rule. So then it's going to be 3 to the n, because I take the derivative of this and leave this alone. And then plus n. And now take the derivative of 3 to the n, so that's 3 to the n times the natural log of 3. Well, that didn't much help. It actually made it look worse rather than better. So I don't think that L'Hopital's rule is really helping us out here. All right. Now what about the ratio test? Or we could use the limit comparison test. Just use what I started with, which was my approximation, and say that is a geometric series that diverges. If I do the limit comparison test, and say take the limit as n goes to infinity, and then you just take one of the functions, so 4 to the n over 3 to the n, which diverges, and then 4 to the n over n 3 to the n, and then this and this are going to cancel, leaving us just with 1 over n, but that's in the denominator, so you need to invert and multiply, and so it's going to be the limit as n goes to infinity of just n. Well, that equals infinity, which means that the test is not conclusive. Start over. That's how it goes sometimes with these. Well, could we do a comparison where ours is bigger than or equal to another one that I know diverges? How about if I put 3.5 in here, and I put 4n here? So 4 divided by 3.5 4 divided by 3.5, that's bigger than 1. So that means if I add up this, it's going to add up to infinity because this is a geometric series with this ratio in here bigger than 1. So I need to then verify, is this inequality true? Of course, I could divide both sides by 4 to the n. I could invert, go ahead and invert, so this is n, 3 to the n, you'd need to invert this as well. 3.5 to the n. And then, let's see, I could divide, so is n going to be smaller than a 3.5 to the n divided by a 3 to the n? Continue over here. Is n less than or equal to a 3.5 divided by a 3 is to the n? So we've now got an algebraic function being compared to an exponential function. So 3.5 divided by 3, so is n less than or equal to a 1.167 to the n function? Since this is an exponential function, I'm pretty sure that that's going to be true. The little n function, is that smaller than an exponential? So if we compare y equals x with y equals 1.167 raised to the x, this would need to go from 1 to 20 or so. I don't think it's going to even take that much to be convincing, but let's see. So there goes y equals x. Is that less than this exponential function? Well, it takes a little while to get going, but this exponential function eventually does surpass Now, whenever we're proving these inequalities, it doesn't matter what happens for the first 12 terms, 13 terms. What matters is in the long term. And in the long term, the exponential function is above the other one. Let's see where that happens, where they cross. So after 19.1, or in other words, from 20 on, the inequality is true. So that means that this series right here, the one that we were given, is going to be bigger than this one, which diverges, and is going to be bigger than this one from 20 on. Not 20 factorial, that's 20 with excitement. So that means that this one does diverge. So since this one, 4 divided by 3.5 to the n diverges, and since we just showed that this one is bigger than that one, then this one diverges also.